Hi everyone, I'm Calvin, co-founder and CTO of Segment. And I'm here today to talk to you about using Terraform at scale and how we've used it at Segment. Now, before I get into that, I'd like to pose the question, what does it mean to use Terraform at scale? Normally when we think of scaling computer systems, we're used to things like managing thousands of instances or dealing with billions of requests per second or managing petabytes of data. But in kind of this post-cloud world, a lot of those things are actually taken care of for us, and they start to fade into the background a little bit. Now, this isn't really to excuse poor architecture or any sort of event where you're not planning for scale, but it does mean that the question now becomes, how do we actually manage all of these resources together? And honestly, there's no better way of doing that than using Terraform, at least in our experience. And so now the question becomes, kind of how do we make sense of all of these hundreds of resources that are being managed for us by AWS or Google Cloud or other providers? And when thinking about this, there's kind of two major scaling vectors related to how quickly you can move as an organization. The first one is the complexity of your architecture. How many different resources are we dealing with? How do they interoperate? How exactly can we move more quickly while still lowering the complexity? And the second one is people. Ideally, we should be able to grow our team, add more engineers to a project, or grow more teammates, and we should be able to move more quickly. But a lot of times, this doesn't happen. And if you've read anything like the Mythical Man Month, you know that a lot of times adding software engineers to a project often ends up slowing it down. And the core reason for that is because of this increased complexity, where the worst case, if you're not careful, actually turns into the average case, where you just have this exponential increase due to the number of people. And instead, where we'd like to get is to something that's a little more linear, or even sublinear, where we can add more people, and they'll actually drive the project more and more quickly, because they're not constantly stepping over one another's toes. So that's the core question I'm hoping to answer with your help over the course of this talk. How do we move more nimbly while continuing to add people to a project? And so in this talk, I'd like to cover three things. First, I'd like to cover our journey with Terraform at Segment, where we started, where we're at now, and where we hope to go. Then I'd like to have a bit of a discussion around what makes for good Terraform. Now, this is a bit of a definition relative debate, but it's hopefully something that we can agree upon in terms of those scaling factors I presented earlier. And finally, a few ideas about what's next in our usage of Terraform and where we'd like to go. So first off, Terraform at Segment. I pulled the numbers yesterday about our current usage, and we're using Terraform actually everywhere across multiple environments. Our current team of engineers is around 25 people. And of those, 16 have actively contributed to our production infrastructure in one way or another, whether it's making changes to individual services, configuration, or even provisioning new parts of infrastructure. We have a little under 100 different microservices running, each of which is provisioned via Terraform. And we have several thousand resources provisioned in AWS, things like load balancers, auto-scaling groups, instances, ECS service definitions, you name it. And we've been using Terraform for about a year. So to kind of set the stage here, we started back in December of 2012, our initial launch. We first started with Terraform about 2.5 years later, over in April 2015. And then after using it for about 6 or 7 months, we had kind of this Redux effort where we decided to rethink a lot of the problems or a lot of the architecture that we were seeing due to the problems we were running into. So to set the scene, a lot of people ask me when I'm talking about Terraform, well, what did you use before Terraform? And to give you a sense of that, I'd like to direct your attention to this painting right here. Now, I can't actually vouch for the fact that there were hordes of skeletons defending our office every time I'd want to change a part of the infrastructure, but I did notice the sky got a little darker every time I tried to boot an instance. And the reason for that was this. Yeah. We initially had a bunch of kind of hand-rolled AMIs that we'd bake every so often, sporadically, when we wanted a new update or a new tool. When we'd actually try and decide to launch those instances, we'd usually take the closest thing that we had and say, launch more like this, and then SSH onto the instance and figure out what was missing from it. In short, it was bad. For those of you who are paying particularly astute attention, you might also notice that our instances were even named after pets right here. Sort of the opposite of the cattle, not pets mentality. But then there was Terraform. And it was like suddenly the world's opened up. In the particular mode of my colleague Rick, he actually has a GIF for this, which feels like sums it up particularly well. It's like suddenly you have this new world with all of this power, where you can suddenly run this command, and it's as if you're able to wield the entire power of the cloud. And so in April 2015, we'd had plenty of this at this point, this munging around in the AWS console, booting up new instances that were kind of like one another, but mostly snowflakes. And we said, OK, we're going to migrate to Terraform and do away with all of this nonsense. And so I was looking back at the first commits, and we migrated in the fairly early days for Terraform. We started by booting up a VPC and kind of all the basic networking parts that you need. And this was back in 0.4 of Terraform. And it was a little bit on the early side. The modules didn't quite work the way we wanted. There were plenty of AWS providers that weren't yet supported. And typically when something would break, the answer from everyone on the Denge team was, oh, upgrade your version of Terraform, and it will probably be fixed, which since then they've done a lot to help the stability of. But in our case, there were two particular things that we did when moving from this really janky production accounts where nothing is version controlled or configuration managed to something like Terraform where it's now all reproducible. And the first one was that we had AWS counts per environment. So what this looked like is that we actually set up completely isolated environments between dev, staging, and production. And we kind of left our old production account to wither and die, basically, and slowly move resources over to it. And we had all these new accounts be managed by Terraform. And we set up this peering connection manually so that if we wanted to talk to the old stuff, we could, but all new things would start going inside these new accounts. And that worked really well for us in terms of actually being able to make the switch confidently and assuredly. Basically, it gave us the confidence to apply new changes at will, since we knew they wouldn't affect the old accounts. And it also let us test the waters a little bit. If you use Terraform at all, a lot of times it kind of seems like an all-or-nothing game in some way, where if you have resources managed outside of Terraform, it might try to delete a VPC or S3 bucket, or something that you really just don't want deleted. So in our case, having an entirely new environment that was isolated and couldn't access the old environment meant that we got really good confidence from actually booting up new pieces of infrastructure. And the second one was moving to Docker and ECS for all of our production services. Now, everyone these days is starting to run with containers and Docker, things where containers can get rescheduled. It's kind of old news. But at the time, it was actually a really good piece of separation for us. It meant that we had a very clean API and separation between working in development and running things in production. Basically, our ops team could say, hey, if you hand us a container, we're going to run it. And on the development side, we could now put our services in Terraform with these ECS definitions, and ECS would handle actually all the rescheduling and running of them. So with that, let's walk through our first attempt at Terraform, which was honestly a little messy. So we had everything inside what we dubbed this infrastructure repo. Had a makefile, standard commands, a README, telling everyone how to use it. And then it had 3 folders, one for each environment: dev, production, and stage. In particular, I'll drill into what one of these environments looked like: stage. Inside stage, we'd have individual Terraform files for each type of infrastructure. We had one file for each sort of AWS infrastructure, which was shared. So these are things like VPCs, S3 buckets, IAM, etc. And then we also had individual files for individual services. So these might be things like our API, CDN, counter service, etc. And you might also notice that we committed our state to Git as well. This was our way of managing the actual state between multiple developers. And for those of you who are unfamiliar, the state is what Terraform uses to track what resources are actually being managed by Terraform in AWS. It's essentially a giant JSON file that's keeping track of everything. And inside each of these files, we had just bare resources. So we'd say, hey, we want to run this version of our app, run with particular environment variables or commands, set up these ports. Pretty standard. And you know, life was better. It's the kind of thing where now we've finally got things rolling. We've got a reproducible setup. But still wasn't good yet. We had a lot of problems that we ran into. The first one of those was environment drift. Basically, what happens when production and stage start getting out of sync? Now, like I said before, we had this environments folder, each with separate files inside them. And what we noticed would happen is we'd have one file indicating the stage version of the app, and we'd have another one indicating the prod version of the app. And this may sound kind of obvious, but whenever you have the same thing defined in 2 places, chances are they're going to get out of sync at one point or another. And oftentimes they'd happen in very subtle ways that it wouldn't be obvious what was happening until far later that we realized, oh, this is actually a difference between stage and prod. At that point, your staging environment is kind of worthless, right? It's not actually reflecting what you want to happen. Second problem was that we had one massive local state for everything, right? It's hosting the entire environment. And so we ended up with a lot of commits that look like this, which are updating the state, updating tfstate, etc. And oftentimes these commits would be particularly hard to parse. They'd be unsure what things they were affecting, and it was all applied locally. And so the general workflow for working with these sorts of things is that you'd pull down or rebase against whatever is on master. You'd run a plan. You'd apply, which made changes to your local state. You'd commit that state, and then push it back up and merge it into master. Now, obviously, with that many steps to do anything, you're going to run into some problems. And in our case, a lot of times the biggest problem was merge commits, or merge conflicts, where one person would either forget to commit their state or not actually make changes, and another person would run into the same issues when they were trying to merge these 2 different versions of the state. It turned out the state problem is really big, too. Here you can see an example of our Terraform state versus Shakespeare's Hamlet. It's about 8 times bigger. Granted, Shakespeare didn't have a lot of ARNs and Amazon's IDs, but all the same, it did make hunting down merge conflicts exceedingly difficult. And finally, because of the state problem, we had this issue with what was actually in Terraform not matching up with production. And the primary reason for that is because Terraform has this target command. Now, targeting seems great in concept, right? It's like, oh, I can just make this one single change to my infrastructure and not have to affect any of these other parts that are living in this giant 8 times the size of Hamlet state file. Well, what happens is at some point you end up with resources that are locally stored but are not applied to production, and ones that are but are applied to production. And you really have no idea at this point where your state lands. It's almost like if you've merged something into master but waited to deploy it, and then weeks later you end up deploying it along with other changes, and you're not really sure what broke. So we took a step back. We said, hey, the setup has some problems. Let's try and fix them. And so we set out to build what we called our Terraform Redux, or version 2. Now, there are 3 problems that I outlined here. The first is that we had a massively shared state. The second is that we locally stored and applied that state and then pushed it up through Git. And then the third is the drift between different environments. Fortunately, there are solutions to all of these problems which have been added in later versions of Terraform. You can split your states up in order to avoid one single massively shared state. You can keep remote state as a way of avoiding local developers planning and applying it. And you can set up modules to avoid drift between environments. So I'll talk about each of these in turn, but first I'll talk about the state management itself. What we decided to end up with here was kind of a hybrid approach. We initially had everything just living in a single state, and we decided, OK, we're going to cordon these off a little bit. We're going to make what we call a core state. And this will have everything with our VPC, our networking, security groups, and auto-scaling groups. This is sort of the fundamental things that the rest of the engineering team can build upon. And the key part of the core state is that it's something that we didn't have to touch often. It's the kind of thing where me and a couple of other Enfred engineers on the team could basically manage this entire state on our own, and then the rest of the team could build on top of it in the service layer. Now, if you're looking at this, you can imagine that each of these boxes here are their own individual state. So while we kept all of these services in their own separate service repo, each of them was still being managed with their own individual state. So if we wanted to make a change, say, to one service, we wouldn't have to worry about it clobbering another. Additionally, we can make this core state read-only. So if any of these services wanted to reference it, they could, but we wouldn't have to worry about them accidentally deleting a production load balancer or bringing down basically our entire VPC. And the way to do this is actually really easy. You can reference this remote state resource in Terraform, say where you want it stored, whether it's via an S3 bucket or Atlas or whatever other provider you're using. And then elsewhere, you can actually reference that and say, hey, I want to draw this variable from this read-only state. The great thing here is that we get confidence about this core state and saying, yeah, this is the up-to-date version because it's living on S3, but I can't make any changes to it and can only reference the outputs from it. And what ends up happening is we end up having basically a folder on S3 for every single service that we're running. So that was the state management piece. Talking about the environment drift gets us into modules. Now, the thing that I hadn't realized initially going in is that when you have the problem of having two separate places where a service is defined, the way to solve that is with a module. Modules enforce configuration parity. If you can't change anything about the way a module is defined, but can only pass in new statically defined variables, you're sure that if two programs or environments are using a module, they're not going to drift out of sync. So for us, that meant modules everywhere. We use them with services. Each environment is a module. Basically, everything is a module so that we can boot it up somewhere else if need be. And what that looks like within our repo is that we actually have this modules folder indicating each different module that we want to use. We have ones for a service. We have ones for a worker, which is reading messages off a queue. But we also have more granular ones for things like IAM users, which also associate a rule and then access keys, or ones for an ELB, which also set up a Route 53 name. As an example, here we've got this Kafka forwarder module, which in itself is a service, and it's got different variables whether it's in production or staging. But it's using the same core Terraform to actually apply it. And then what that Terraform looks like inside is it's actually pulling another worker module from outside and setting up those events properly. What it means is that all a developer has to do is supply a Docker image that they want to run, a version, and any command line flags that they need, which there are probably too many here, honestly. And then from there, they can get up and running. So that's Segment's Terraform evolution. And from there, we wanted to figure out kind of, if we were to do it all over again, what would make for good Terraform? Some definitions of good. I think it depends a lot, depending on what size you are as a company, what sort of Terraform will work for you. So for us, our answer to this was this project that we open sourced and put on GitHub that we called the Segment Stack. And the goal with the project was to provide you a set of production-ready AWS infrastructure that you could boot using entirely Terraform. And all it is just a bunch of Terraform modules that wrap various components of AWS. So it'll set up a VPC, it will set up multi-AZ networking with different subnets, it will set up an auto-scaling cluster that's hooked into ECS, and it will set up a Bastion node in case you want to SSH into any of them. And kind of the fundamental piece for this was building a standard AMI using Packer, which just runs Ubuntu with systemd on top of it. And then systemd is supervising Docker and the ECS agent within it. And it's pretty cool how just using this like very primitive set of AMIs, you can actually get Amazon to do most of the work for you when it comes to actually running your services. Because now you just define the services in Terraform, and then ECS runs them for you. What this looks like elsewhere is we have our cluster instances, which are set as part of an auto-scaling group. Each of these are referencing that AMI in the last slide. And then from there, we have individual containers, each of which are scheduled via an ECS service. All of this is built via our service Terraform module, which I can walk through in a second. And additionally, we set up an ELB, which does the load balancing between individual containers. And from there, we use DNS for service discovery. So the two key, or I guess there are 4 key aspects to Terraform here. I'm not sure why only 2 of them are showing up, are your variables, your composition, and your versioning for modules, as well as, I'm not going to remember the last one, but we'll get to it shortly. So for variables in modules. Variables initially seem like kind of a scary thing from configuration management. You wonder, like, what do I make a variable? What do I just hard code in? What should I do to kind of manage the state? What things should be remote state? In our experience, we found variables are really just like any other program, operating system, database, anything else you're running. Anything a user might want to override should really be a variable. And that way it gives you flexibility so that if you're using that module elsewhere, you can always change it around. Now, if you've seen Terraform modules which have crazy amounts of variables that they require as input, that's not very fun either. So to combat that problem, we use defaults very liberally. And we actually use module composition to help make it so that if you're a developer, you have to pass in kind of the minimum required config you need to get up and running quickly. But if you want to, you still have this escape hatch of overriding everything. And so here, we can see that, oh, the slide got a little messed up. We can see that we're booting a Bastion instance, and we have several pieces of configuration that are actually configurable, but several that are not. And they just live on the resource itself. Here, perhaps a better thing to do would actually be to convert everything into variables and then set those defaults to false. So if the developer wanted to override them, they could, but they don't have to by default. The second piece I'd like to talk about is composition. How do you compose modules? Which is one of the first things that was really hard for us to grok and get our minds around. In our experience, we found it best to build modules as you need them. Remember, a module is just a group of AWS resources. It doesn't really need to initially be over-abstracted or kind of say, hey, I want this module and everything is going to use it. Honestly, because you have this escape hatch to declare resources manually, it's kind of OK if not everything fits within your abstraction. But we basically found, after rewriting the same set of resources over and over, that we wanted kind of the set of modules to build upon at a higher level of abstraction. And I can show you what I mean. Within this stack module, we can reference it just via the GitHub segment.io stack repo. And inside, we can pass in the required variables, which would be things like the name or environment. Now, if we dig into what's going on inside this module, we can see that it's only just one Terraform file. And inside, it's actually just referencing a bunch of other modules. And so if we want to get this full stack, it'll boot up the VPC, it'll boot up the security groups, it'll boot up the bastion, and each of those can reference each other's outputs. But what's great about this is that it actually doesn't force you into using that top-level module, right? Since each of these are built upon these kind of sub-module ideas, we can actually just reference those if we'd rather bring our own VPC implementation, or we'd rather bring our own security groups. The great part about this is that none of these are tied to the specific stack implementation because we can reference them independently. I already touched upon the state management a little bit, but essentially, if you're using Terraform with more than one person, you're going to want to have some sort of remote state. Other than that, it's OK. And this, I think, is often a tripping point for teams because Terraform often starts with one person, and one person's working with it and got a very good sense of how to work with it. But what happens is quickly, the moment that you move to 2 or 3 people, sharing that state becomes unwieldy, unless you're using something like Atlas or S3 to store remote state. Additionally, we've had very good luck having a state per each individual service. It means that if I'm working on a particular service and my teammate is working on a separate one, we can be 100% guaranteed that changes to that service's configuration will not conflict. And finally, we output binary plans as well so that we can at least check and see whether the state has changed from one version to another. Now, we don't actually have locking on these plans going yet, but that's something that Atlas provides and is something that we'll be investigating more in the future. And finally, there's versioning. This is actually a little known feature of Terraform that I hadn't anticipated at first. And it's only after using it pretty heavily that we've managed to dig ourselves into a hole by not doing versioning. Basically, when you're referencing a particular module, you can actually append a ref tag to it, and it will tell you either a git SHA or a branch or a tag, or really any of those, which point to a particular definition of the module. And what that means is that you can actually version your configuration and the modules that it's targeting, rather than just kind of hoping that you're always targeting latest and no one's changing anything on the other side. And this is something that, honestly, we haven't gotten right yet, because we've stored all of our modules in the same Git repo as the one we're planning against. And what it means is that if someone makes a change to that core module definition, we end up having to just upgrade to latest all the time, rather than being able to upgrade services kind of at will. So I'd highly recommend, if you're building modules, kind of once they've reached a state of stability, break them out into their own GitHub repo or set of repos, and then from there, version all of your application code against them. So I'd like to wrap up with a few ideas kind of about what's next here and what we're thinking in terms of next steps for our Terraform setup. Well, right now, everything still applies locally, which is not great. The convention here is that if you're a developer on the team, you make a pull request, someone else reviews it with the plan, and then at that point, you're ready to apply it. Of course, what that means is that, one, it's done by convention, so at some point, it's going to break. And then two, we don't actually have a great record of those things getting applied. Apparently, you can do the same thing in Atlas, which is something that we're going to be checking out more and more, but having at least CI responsible for outputting the results of plans and then applying them elsewhere would be a very handy thing to have. Another question that people often ask me is for things like deploys. Do we have to go through Terraform for everything if ECS is managing the state of our currently running code? And honestly, at Segment, we do something that's a little bit hacky for this. Since we haven't upgraded to Terraform 0.7, we haven't started using data sources yet, which I think would ultimately just fix this problem for good. But right now, what we do is we actually deploy outside of Terraform and pin Terraform versions to a 1.x version. When we have builds, we'll build not only the Semver version, so 1.4.x, but we'll also, or 1.4.6, let's say, but we'll also push up builds for 1.4.x, and we'll also push up a build for 1.x as well, basically overwriting those old builds, but ensuring that we can do a rollback if need be. And finally, there's this idea of Terraform generation. Now, if you're like me, you've probably tried to use Terraform for something, and you kind of run up against a wall a little bit, where Terraform's configuration language isn't as flexible as you'd like it to be. And honestly, I go back and forth on this, because there are a lot of nice properties to having something that's statically defined, automatically creates a DAG, results in all the dependencies that you need. But on the flip side, it would be nice to have something like, say, conditionals, where you could selectively apply parts of the infrastructure to your module, and then depending on a flag that was passed in. And obviously, this breaks the whole idea of getting parity from modules, where now, if you have two different versions of a module, you're not going to actually have the same behavior. But it does make an interesting question. What if someone built, say, a DSL or tiny service generator over this, which allowed you to output Terraform kind of selectively? This is something that we'll probably do internally at Segment, just for generating actual module definitions. But honestly, I have mixed feelings when it comes to actually adding sort of language-level extensions. So if there's one thing I'd like to leave you with today, it's circling back to that question. How do we continue to add people to our system, or get more people on our engineering team, and still move more quickly and more nimbly? And I think the key answer here, at least in our experience, from everything that we found, really comes down to isolation. Whether it's your individual microservices, your state that is shared only per individual service, your individual AWS accounts which can't talk to one another, or your projects that your engineering team is working on, basically you want a single engineer to be able to come in and tackle some new project or some new feature. And you want them to be able to run ahead as quickly as possible without having to go through 5 or 6 different other teams. And for us, the biggest things that have helped there are, one, having kind of this public access to Terraform, where everyone can boot their own services, and it's very democratized when it comes to creating new forms of services. But the second is also working with Docker, where now we have this clean API where people can essentially just boot new containers in production without having to worry about the provisioning setup for them. And with that, I'd like to thank you all for coming to this talk today and listening to me babble about various forms of Terraform in isolation. If you have any questions or additional thoughts or comments, I'd love to talk to you more after the break. Thank you. We're close. The question was, have you ever decommissioned the old prod account? This is something that's weighed on me for like a year, honestly. I think I'm going to make shirts whenever we do finally get rid of it. We're about I want to say 95% of the way there. Initially, the hardest thing with decommissioning it was actually Segment is an analytics company where we basically pull in data from a lot of different places about your customers and then put it in one place. And as part of that, we'd offered this product offering of hosting Redshift for various customers, where we say, hey, we'll give you a data warehouse, no action from you required. And getting customers to move off of those Redshift instances in our old production, which were using an old pipeline, to the new one was pretty nightmarish, honestly. And then we have things like S3 buckets, which it's unclear how we're going to move like those petabytes of data unless we really want to. So yeah, still working on that one. Yeah. What's our test coverage? So we don't have great test coverage on the Terraform itself right now. We predominantly use staging as the sort of integration test environment for Terraform and kind of verify that everything looks good, and then from there we can apply those changes to prod. Feature branches. We do in a few areas, primarily in that app itself. So for that, we're using Split IO, I think, for actually managing kind of features. And then we also have a separate canary setup that the entire, just people at the office are hitting. And canary itself is also a Terraform module, so it's pulling from the same thing as app and what's being served to the rest of the world in production. But it helps us get a little bit better kind of coverage there. But nothing other than that yet.
So you put your Terraform states in remote S3 bucket, right? And each service has its own code. And but S3 doesn't really give you a locking method, right? You still has potential people try to touch the same states file.
Right. So the question was, even if your state is stored on S3, S3 doesn't give you locking. So what do you do when two people are trying to access the same state file? So there are kind of two ways that we get around this, and honestly, neither of them are as good as the locking that Atlas will provide you. So if we have to do it all over again, we might choose Atlas instead. I think we ended up rebuilding like 80% of Atlas on our own, kind of by accident. But the general idea is that we output a binary plan. So it will basically check the existing version of the state and then output a plan which I think should apply. Basically, Terraform keeps a serial number for the version of the state. And so it will then only apply if the serial number kind of matches and there hasn't been a change within there. That said, it is possible if like two people are both kind of planning and then making changes that we could run into a conflict. By having a state per service, in our experience, it doesn't really happen.
Yeah, I asked around and it seems people using procedures.
Yeah.
I have a general comment because this is by far the most interesting talk to me. And
Thank you.
I would love to talk to people about these problems like CIC of Terraform is something we're going to be delving into in a couple of weeks. So like anything advice-wise that you guys have for this, we went through those various things.
So we're kind of going through the same stuff. So you guys can for lots of them use this tool called Terraform, which uses CCC's dynamic view to do a lot. And it just kind of wraps around Terraform and says all that just kind of
Oh, awesome. What was it called?
Terraform. It's on GitHub. It's free.
Cool.
What's it called? Terragrunt?
Terragrunt?
We also use it. So just also an additional comment and a question. We just started a while ago building out a new platform, and we actually have used your stack as a baseline for building our own stuff. It's
Oh, awesome.
really helpful as kind of a starting point. We don't use it directly, but we copy and paste and then sort of build our own stuff off of it. It's been really helpful in accelerating that. It's been awesome. One breakpoint that we made was that we were only managing up to the ECS cluster struggling to find sort of the cost-benefit analysis of using Terraform at the service level. And I can see being able to talk to the remote state and get stuff there as a benefit, but are there any other benefits you get from
Yeah.
Terraform do the service deployment itself?
Yeah. So I'm not sure what your shell scripts are doing, but at least in our experience, the nicest thing is actually just sort of like traceability, where if you're looking to figure out where a service is running, how a service is running, kind of like what it's doing, and maybe like the changes in that over time, it's really helpful to just go and look at the definition and then look at the commit history for that service. Yeah, it does get a little bit clunky in some ways because Terraform is more or less static, and like things with services, you tend to change them kind of all the time for deploys, et cetera. But yeah.
Have you guys managed capacity addition with any changes that might be included when you turn up new capacity or take away new capacity?
Yeah, we don't have a great answer for that right now. Basically, everything's running in an auto-scaling group, and we set the desired count in min and max, and then it will drift, and so yeah, that's something that we still have to figure out.
Okay, Calvin, awesome talk, and
Thank you.
Thank you so much. Really appreciate this.